Hey, quick question. Given a dataset of billion images, is it possible for you to rightly classify them into one of the 300,000 types of plant images? Wow, not that easy. Alright, given thousands of images displaying numbers, is it possible to you to rightly classify them into one of the 10 digits? The task specified would be intuitively straightforward for we humans, but hard to be formally described as a set of rules for the machine to process information. So for a mathematical model to work on problems like these, its network has to be loosely analogous to the architecture of a human brain. The closest to that which exists in today's technology for image recognition or convolutional neural networks. With the aid of convolutional neural networks, it is possible to predict the image with a pretty decent accuracy when compared to other mathematical models. Here's with a simple example from which I would amplify it to a bigger one. The MNIST dataset is a collection of thousands of size-normalized handwritten digits centered in a 28 by 28 resolution image. The 784 neurons from the 28 by 28 pixel image make up the first layer of the network. The last layer contains 10 neurons, each representing one of the numerical digits from 0 to 9. Let's start with the grayscale image. There is a range of monochromatic shades from black to white, represented by a set of rational numbers from 0 to 1. The input layer consists of a set of neurons corresponding to each pixel of the input image. The neurons generally hold a number between 0 and 1, which represents the grayscale value of the pixel. These numbers are generally called the activation number, and the neurons containing values beyond the threshold value tend to be activated. The output layer is a set of neurons representing the desired output for our problem. The numbers in these neurons represent its probability of being the desired output. The layers in between the input and the output layers are called the hidden layers. The neurons in the hidden layer hold certain values known as weights, which influences the predictability of the model. These weights are sensitive to the cost function and are updated by backpropagation. The types of hidden layers I want to talk about are the convolutional and fully connected layers, which are generally present in the hidden layers. In fully connected layer, each of its neurons are connected to the neurons of the next layer. It contains about 5 to 10% of the computation, about 95% of the parameters, and have small representations. Fully connected layers can only deal with inputs of fixed size because it requires a certain amount of parameters to fully connect the input with the output. The convolutional layers just slide the same filters across the input, so it basically deals with the input of any arbitrary spatial size. The convolutional layer cumulatively contains about 90 to 95% of the computation, about 5% of the parameters, and have large representations. The penultimate layer, that is the layer before the output layer, is generally a fully connected layer. The larger the amount of images supplied, the prediction accuracy of the model increases. Since the process is computationally intensive, it's essential to analyze the scope of parallelism that can be involved in the model. Across the data dimension, when the workers are allowed to train on different data samples, it is known as data parallelism. Here, the workers must synchronize the model parameters or the parameter gradients to ensure that they are training a consistent model. They are efficient when the amount of computation per weight is high because the weight is the unit being communicated. Consider that a neuron can store up to 4 bytes. For a smaller network as shown, the amount of storage required for these last 2 layers of the model will be 640 bytes of storage space. Then what about a neural network that has to classify 300,000 types of images? In our case, we used a standard ResNet 50 model which has 1024 neurons in a fully connected layer. Therefore, the amount of storage required for these last 2 layers of the model will be approximately 2 gigs of storage space. And considering only data parallelism in this case, each worker has to share the complete model. And here's where model parallelism comes into play. Different workers train different parts of the model. They are efficient when the amount of computation per neuron activity is high, because the neuron activity is the unit being communicated. By exploiting these 2 different parallelisms combined, we obtain better scaling. The current convolutional neural networking models utilize data parallelism in order to scale up and handle large training sets. The inability in further compute time reduction beyond certain compute capacity and the requirement of larger training datasets is benefited by the inclusion of model parallelism. In this ResNet 50 model, the fully connected layer is split among the workers, thereby making the computation less intensive. The entire model is implemented using TensorFlow and Horvath libraries in Python. In order to measure the run times, the TensorFlow and Horvath timelines are used. For convolutional and fully connected layers, the forward and backward computation time with respect to the layer inputs and the backward computation with respect to the filters separately are tracked. The data parallelism approach for training the model using up to 4 GPUs with a weak scaling strategy is compared with a hybrid model where each of the 2 CPUs connects to 4 GPUs.